Hello everybody, hope you're having a good day today, and today we're going to be doing projectile motion / kinematics practice questions. I have 3 questions here today, and basically I'm just doing practice questions just to obviously to practice, right, to get better at what we learned in the previous videos. And if you haven't checked out the previous videos, there'll be links in the description below, or you can just go to my channel page and find the videos. And so I hope you're excited for this, and I hope you're ready to practice and improve our skills. So let's get to it. Alright, so let's get started. So this is our first question here, and you can pause the video to read the question if you want, or even try it, right? Just pause and try it, see if you can do it, and otherwise I'm going to be going over the solution right now. So first of all, so this question is first of all asking us that, well, it's first of all telling us, right, there's a rubber ball that's bouncing on the ground, right, and every bounce it reaches half of the height that it was, like half the height of the previous bounce, right? So if this was like 6, for example, let me get a different color. If this was like 6, so this would be like 3. So it's bouncing half the height. Now, knowing that, we want to basically find the time between the second bounce and the third bounce. And we're given that between the first bounce, so I'm just going to write it like t1 to 2. So the first and the second bounce, we know it's 1 second, right? Now, we're trying to find what time it takes between second and third. So how would we approach a problem like this? So first of all, we know that it was just released, right? The ball has to be released in order to hit the ground, right? So that means our v initial must be 0, right? We can assume that because it was released, and so there was no initial velocity, right? We're not assuming that they threw it down or something. We're just assuming it was released. Now, since we know that the displacement y, delta y, is now going to be equal to 1/2 at squared. Or actually, let me just write all the steps so it makes more sense. So we know from our big 5 or big 3 formulas that it'd be VOT plus 1/2 at squared, right? Now we know that VO is velocity initial 0, so that means this is just going to cancel out, and we're just going to get the change, or like the height, is basically 1/2 at squared, right? Now, since we know that, what we're going to do is we're going to solve for t here, actually. So what that's going to be is it's going to be at squared is going to be 2 times delta y. So I'm just basically multiplying the 2 on both sides, right? And then t squared is going to give me 2 delta y over a. And then you're going to get that t is actually going to be square root of 2 delta y over a, right? So that's what our t actually is, right? If we were just solving like this with our height going up to the full potential, right? So at like this point right here at the top. But what we're given as the question is that we want to find half as much, right? So that means we want to find half of delta y. And what that means is we're going to basically again solve for 1/2 at squared, because that's just going to give us the displacement, right, in the y direction that we're going, right? So again, doing it this way, again, we're going to multiply 2 on both sides, but it's actually going to cancel out the 1/2, right? So that means delta y is 1/at squared, and then t squared is delta y over a, and then you get t is root of delta y over a, right? And looking at this, it's kind of like, what did we just get, right? Like, what is this? Like, how is this going to help us find a numeric value? Well, let's relate it back to our previous formula that we found, or derivation that we found. You see that here we have root of 2 times delta y over a, and you see this is just delta y over a. So we see this root 2, right? Or this, the 2, right? And we have to think about it, like, how can we use that to our advantage? So here, what we can actually do is we can pull the root 2 out, right? We're basically using basic math. We're going to get that root 2 is, this is basically root 2 times root delta y over a, right? So that just means that basically what the previous, or the original time, if you relate it to this, is that our original time is just root 2 times whatever this time was. And let me just give these like actual, let me just like make a difference between them. So let's say this was t2 and this is t1. So what that means is t1 is just root 2 times t2, right? Or that also means that t2 is now going to be just t1 divided by root 2. Okay, so that helps a lot now. Now, we were given that t1, or t1 is 1 second. So that just means that t2, let me erase some stuff here actually. So I'm going to actually erase this part, this derivation part, because we know how to find that. So I'm going to bring this t2 over here just to give some room. So we got that t2 is t1 over root 2. And we know that t1 is 1 second, so that means t2 is just 1 over root 2. And if you were to put that in your calculator, you get about 0.71 seconds, and that's option B. So that's how you would do this. You have to do some manipulation with the variables and also derive the variable for like time, for example, and then realize that this root 2 is just this t1 and t2 are very related if we just pull out this constant root 2, right? So that's how you would do this problem. Let's go on to the next one. Alright, so this is problem 2. Again, if you want to do this problem, just pause the video and like try to do it, and if you don't understand, check the solution right after, as I'm going to present the solution right now. So how we would do this problem? So it's saying that there's a free fall object and it's thrown horizontally from top building, which, okay, we get it. Basically, it's telling us that it's a projectile motion problem, right? So, and it's saying what set of arrows best correspond to the direction of velocity and acceleration for at that point. If you remember our last video about projectile motion, we actually basically talked about this, right? And if you don't know, please check that video out. I'll put the link in the description. Basically, in this case, right, we see that it's on the downward, it's falling down, right? This P object, it's going this direction, right? It's just going to fall down, right? And we know that acceleration and in projectile motion is gravity, right? Gravity is our acceleration. Now we know gravity is always pointing downwards. So that just means that acceleration is downwards here. So that just gave us the first option. Now we can eliminate C and D because none of them have acceleration going down. So it's between A and B here, not A and B, right? So make sure that you always cross out answers that you know just are automatically wrong, right? Because you don't want to be thinking about them just by mistake select like C or something because you got confused at the end. Now let's think about this. Now we want to talk about velocity, right? Let me choose it. Not yellow. Let me choose. Okay, so let's think about velocity. Last time we talked about it, right? Velocity is basically going to be like the vector sum, right? The vector sum of the velocity in the x direction and the vector and the velocity in the y direction, right? That's going to be our velocity. Well, here our x direction velocity is always going to go horizontal, and y direction velocity in this case is going down, right? Because we're going down. I'm going to just draw an arrow next to it, right? So this is also going down. So that means our vector sum, if we were just do some basic vectors, right, it would just be in the direction of the motions. It would be this direction right here. And that would be the direction of our velocity. And if you remember that diagram we did last time, you just remember right off the bat, oh wait, velocity is just direction of the motion here, right? So that means our velocity is this. So that means A is correct. On to the next one. This was a pretty small problem, right? But just this is a good problem to see, to check your concepts if you know what direction the vectors are. Anyways, on to the next problem. Alright, so our final problem, which is actually a bunch of problems, and in fact, this problem is actually old AP Physics FRQ. So FRQs on the AP Physics are the free response questions, and they're usually something that a lot of people struggle with, and they're all usually hard as well, right? So they're not like easy problems. So this is FRQ, and this is a projectile motion FRQ, and I think it's from 1994. Yeah, it's from 1994. So it's an old one, but it's still a really good practice. So let's talk about it. So if you want to try it and pause the video and try the problem out, go ahead. But here we go. So these are the solutions. So first, we see that they're giving us all the sign values because they probably don't want us to calculate it because there might be errors, but we're right. We have to use those values. So don't forget that. Usually when you see this kind of thing, you want to box it because sometimes, you know, you're in a rush, you're trying to do the calculation, you're just going to do whatever the calculator has, right? Just make it simple for yourself and don't make silly mistakes by just circling and just knowing that, yep, I need to use these values. Anyways, we have a ball that mass 0.5 kilograms, initially rests, basically getting kicked away, right, at an angle, so projectile motion, and the top of the fence is 2.5 meters tall. And, well, basically it's basically telling us there's no air resistance, which you won't have to deal with in AP Physics 1, and and the ball hits nothing in flight. So nothing's actually affecting the ball, it's just gravity right now. So basically now, first question is pretty simple, right? It's just asking, determine the time it takes for the ball to reach the force. Now, remember, we talked about it. Whenever you're doing projectile motions, you want to make an XY table, or XY table, right? So I'm going to create an XY table, and I can find my velocity X and my velocity Y. Velocity X, in fact, actually, let me make this a little bigger so I can have more space here, but here, our velocity X, right? So X direction, Y direction. Now, our velocity X here is this 20 meters per second, right, which is the initial cosine of the angle. Remember that X direction you're using cosine, Y direction you're going to use sine, right? And depending on what angle you get, sometimes it's really weird, but you could get something like this, and that case would be sine, but you could always get to this angle, right? Just 90 minus whatever this is. Anyways, getting off track there. Anyways, Vy here would be 20 sine 37, right? So oops, 37. Let me write that a bit better. Anyways, this would be 20 sine 37, right? So actually, if you recall our kinematics formulas, we remember that the displacement in the x direction is velocity initial x times t, right? And this is the easiest way to find time, because we're given that this distance right here is 32. That's the displacement that the ball is actually going to go, right? Now, 20 cosine 37, they've given us is 0.6. So if that's 0.6, or it's not 0.6, 0.8, sorry, I read the sign there. That's 0.6, that means our velocity x is 16 meters per second, right? You just do 20 times 0.8, right? So here, that means we can just plug everything in, right? So delta x is 32, velocity x is 16 times t, giving us t is 2 seconds. And that's just the easiest way to find time. So you already just got one of the FRQ questions correct, right? Just by basic formula application there. Okay, let's do part B now. So let me just erase this stuff. So part B is talking about how when the ball will hit the fence. So we want to find basically, or no, not when, we're asking will the ball hit the fence, and we want to figure that out, right? So we want to figure out if the ball will hit the fence, that's the first thing, and then we want to see how far below the top of the fence it will hit, if not, how far above. So we just want to find where, if it hits and where it hits, like what's the position. So to check if it hits, we need to make sure that this ball, right, as it goes, it is able to travel a certain distance. Basically, we basically need to find the delta y at the first, like the angle. Okay, so basically what we're trying to find is, here we want to find, you know, the ball is going to go in this arc, like an arc path, right? Because it's projectile motion. Now we want to use what we got from A, which was 2 seconds, right? That was the time it takes to get past 32 meters, right? That's where the fence is located. We want to find the delta y of, or the height at which it hits the basic 32, like after 32 meters. We want to find that y position, and if that y position is between 2.5, like 0 and 2.5, that means we know it hit the fence. If it's not, that means we know it didn't hit the fence, and we get both our answers at the same time. Now that means we use one of our big 5 formulas, or here in this case we're using delta y instead of delta x, right? But the property stands. So delta y is going to be equal to VOY t plus 1/2 AT squared. Now, since we're doing in the y direction, our A is going to be g, right? And I'm just going to write that here. Our A is going to be g, and our VOY, if you remember from the XY chart I made, is 20 sine 37, right? Sine 37 they given is 0.6, so that just means our VOY is 12. And let me actually write that here, so we can get the space just for solving. So that's 12 meters per second, right? And make sure you write the units so you don't forget, just in case, right? And oops, the y. Okay, anyways, so delta y, right? We want to find delta y. So that's just going to be plugging everything in, right? So we got 12 meters per second times the 2, which we found in A, plus 1/2 g, which is negative 9.8, remember, because it's downwards. And then the time was 2 seconds again. So let me just write the point there. So that means our delta y, if I plug it into a calculator, right, would give us, so again, so 12 times 2, negative 4.9 times 4, what that would give us is 4.4, right? That gives us 4.4 meters. So that means it doesn't hit the fence, right? Because it's greater than 2.5. And what point it hits is 4.4 minus 2.5, right? Minus 2.5, which gives us 1.9. So it hits 1.9 meters. I might have said 1.5. 1.9 meters above the fence. So that's our answer for part B. Now let's talk about these graphs. So again, I'll erase this, right? I think a good color for this would be blue, so you can actually see it on the paper, because we're just going to draw the graph right on top of this. So first graph it wants is Vx, right? This is velocity x, horizontal component of velocity versus time. Now we know that from our normal concepts from projectile motion that Vx is always constant, right? It's always constant because it's never changing. So that means from what we found, Vx was, again, it was 20 cosine 37, which they gave us 0.8, which was 16 meters per second. So that means it's just going to be a horizontal line. I'm going to try my best here. So 16 was, oops, that's not 16. 16 is right there. Okay, that should be good. Hopefully straight. Yep. So this would be our line. Obviously not this part, right? You don't want that outside part, but that would be our line, right? That would be our Vx times velocity because it's constant, right? Velocity isn't changing, and so that means this is our line for Vx. All right, so let's do Vy versus Vy versus t, right? And so this is vertical component as given right there, and so we know Vy at the start we got was 12 meters per second. And we know that Vy is going to keep increasing, not increase, it's going to keep decreasing until it gets to the max, where V is 0, Vy is 0, and then it's going to become more negative. So knowing that means we know we got a downward sloping line, right? Because it's going to be positive and it's going to keep decreasing all the way down. So since we got that initially, that Vy is 12, we know we start somewhere around here, right? Somewhere there. Then we get a downward sloping line. So we can actually just make it, I'm going to make it a bit more accurate by making, that means at t we know that our velocity is 0, right? So we're going to be accurate, right? We're going to find actually the time where velocity is 0, or time where velocity is 0. So how we can do that is we're going to use one of our big five, which is Vy is equal to V0 initial plus GT, or GT, right? But G is going to be negative 9.8. So this is going to be 0, this is going to be 12, this is going to be negative 9.8 t. So solving for that, you get t is around negative 12 over negative 9.8, giving us around 2 seconds, or 1.2 seconds, right? I'm just going to round it. So that means somewhere here, oops, not there, but somewhere here, right? So that means we can just draw a line, like, so if I were to draw a line, which I can't draw for some reason, okay, that was a horrible line, but it's close enough. This would be something like that. And that would be our Vy versus t curve. That looks like an Vy versus t curve, right? Alright, so I hope you enjoyed this. This was actually an official FRQ question, and we actually went through it, and I explained the process to you, so I hope you got that. So let me know what you want to see in the comment section below. Let me know if I missed some of the parts, or if I missed like I didn't explain properly or something like that. So let me know in the comment section below. Next video, we're probably gonna jump into dynamics, we'll jump into dynamics of forces. This is essentially a kinematics unit. There is circular motion in kinematics, but I feel like that would be better if I go over that in the actual circular motion or the forces unit, the dynamics unit. So dynamics unit's actually pretty fun. This is also pretty fun. Let me know if you want to see any more like practice videos on projectile motion. I'll probably be making, like, at the end we'll probably do like run through like 5 different problems, and it'll be like one from kinematics, one from dynamics, all that kind of stuff. So let me know if you want to see that in the comment section. Please like the video if you haven't. Please subscribe to the channel, and as it helps the channel, it pushes it out. So I hope you enjoyed this video, and I hope to see you soon. Thanks for watching.